Hello everyone, welcome to the OneClass channel and good morning. My name is Fejiro and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked questions both at the high school and college level. If you're looking to get some just extra help or an extra hand in regards to these topics, please check out the links in the description below and we'll be more than glad to help you. Okay? Now, with the formalities out the way, we're going to begin our session for today. This is going to be with the first question being, depict the electron configuration for phosphorus using orbital, box, and noble gas notation. Give one possible set of 4 quantum numbers for electrons beyond noble gas. So this is definitely a bigger scope of a question. Nonetheless, we will tackle it right away. So the question asks for phosphorus, okay? So on the periodic table, phosphorus is the 15th element, okay? So I'm going to go ahead and start writing out our electron configuration numbers. So we have 1s, 2s, 2p, 3s, 3p, 3d. I'm going to stop here at the 4s because as you'll see for phosphorus it doesn't even get past 3p. But how do we count this? So hydrogen and helium, okay, because helium is the only exception, even though it's a noble gas, it counts as being on the s orbital. That will be clearing your 1s. So we're done with that. We actually at least have 1s2 because hydrogen then helium. Then 2s, okay, 2s1 is lithium, 2s2 is beryllium. Okay, so we've cleared through that. We're in a sense counting through each element. Okay, and then following after we have boron through neon. Okay, these starting here from column 13 through 18, excluding helium, that's your p orbital. Okay, so because it's a second row, we have 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So we've cleared that row. Then we hop to the next row, the third row. Okay, we have sodium, magnesium, that'll be your 3s2. And then we finally get to close to where phosphorus is. And similar to what we just did for the earlier row, we have 3p1 on aluminum, 3p2, and 3p3 for phosphorus. Okay, so this is where we stopped. All right, and this right here is your electron configuration for phosphorus. Now, if you wanted to get the noble gas notation, what you would do is this prior part, if you notice, that actually accounts for neon. So you'd replace that with this type of notation here, allowing you just to write what comes after. And this is your noble gas notation. As you can see, it makes it quite distinct which your valence electrons are. Because considering phosphorus is on the 15th column, you can see here that it indeed has 5 electrons in its valence shell, based on the fact that the superscripts here, 2 and 3, that adds up to 5. That's where you get the value from. So this question doesn't only ask for that, but also the orbital box notation. So for this, what we do is because they want to know orbital box for the whole thing and the noble gas, we're going to first draw out our boxes. Okay, so just as how I have that above with this breakdown, it's going to be the same thing, but as you notice, I'm adding more boxes here because as we're counting, you see that the s orbital had 2 elements each time, right? That's because it counts for 2 electrons. As you go to the right on the periodic table, you're adding electrons, right? So this is your S shell. Same with these, but this will be significant of your first row, second row, and then we have the third row. So like this. Sorry. We have like that, okay? And then we're also going to add the shorthand version with the noble gas. It's going to be similar to the 3 we have there, but exactly just going to start like that. Okay, and it's just going to be 3s because now we still should indicate at least what what row we're on. Now let's start actually filling these boxes. So for 1s, as we discussed, it goes hydrogen, then helium. Okay, that's how you fill that up. And then we have for the 2s, we have the lithium and beryllium, I believe. Yep, lithium, beryllium. And then to clear this row, the way it gets filled up is like this. It goes boron, carbon, nitrogen, then oxygen, fluorine, neon. You see how I filled that up? That's because each subshell likes to be half filled first before it fills up completely. Same thing here. We have the 3s representing the sodium and magnesium, and then, as you probably guessed it, aluminum, then silicon, then phosphorus. Okay, that is what we'd have. So with that being said, this neon would just reflect, this shorthand will also just reflect what's above. Okay, so we'll now be able to draw out our orbital box notation as well. So now it asks us to give one possible set of 4 quantum numbers. So the 4 quantum numbers they refer to, okay, are n, which represents your number of the shell you're on. So, well, the row pretty much, which is the number of orbital. Okay, so right now, if they're asking for electrons beyond the noble gas, as you've noticed, they all have that same number 3, okay, beyond the noble gas, because now we're dealing with electrons in the 3rd orbital, the 3rd shell. Okay, so that means for all these here, we're actually going to be extra and just list out every possible combination of every electron in this. So because there's 2 in there, there's 1 in here, n is going to equal 3 for all these. Okay, and now L is the type of subshell. Okay, and what I mean by that, they go through rules. Okay, if L is equal to 0, that's the S subshell, the first 2 columns. If L is equal to 1, that's the P subshell, which is columns 13 through 18, excluding helium. If L is equal to 2, that's your D subshell, which is columns 3 through 12, okay? And if L is equal to 3, all right, that will be your F subshell, which is your lanthanum and actinium series. And as you notice, okay, is that typically the N, the number of orbitals, will always be at least 1 greater than your L. Because, for example, hydrogen, okay, it's in the 1st orbital, but that means because they only have the S subshells there, you're only dealing with 0 at the L. So with that being said, for these, the L's here would be 0, 0 as well, and here would be 1, 1, 1, because these 3 here are in the P orbital and these 2 here are in the S orbital. Now ML is possible combinations. Well, instead of putting that can be a little bit abstract, it's going to be positive and negative of L, okay? So in this case, all right, because L is 0, ml, okay, is going to also be 0, because positive and negative of 0 is going to be just 0. Now here, okay, we want to list out all the positive and negatives. So we're going to assign them, and it's up to you how you want to assign them. I'm just going to start like this. So ml here for me will be positive 1, okay? Here, ml will be 0, because you want all positive combinations, so it does include 0 as well. You want to go from the negative to the positive value of L. So here, if you probably guessed it, ml will be negative 1. So we have positive 1, 0, and negative 1, okay? And for the last one, okay, ms is just type of spin, okay? And it could only be represented by positive 1/2 or negative 1/2. And typically we represent the arrows pointing up as positive 1/2 and the arrows pointing down as negative 1/2. So with that all being said, our ms for this, considering that we're referring now to the first electron here, will have that positive spin theoretically, okay? Our ms here will have a negative spin because it's pointing down. And as you notice, all these ones here in the p orbital are pointing up. So all the ms's here would be a positive 1/2. Okay, so I know it only asks for us to list one, but the key reason why I listed all of them is because if you notice, right, is that if they were saying list something from the p orbital in terms of their I always forget the word, the quantum number, it's key here to recognize that if it was in your p orbital, you would not have a negative spin for phosphorus because that is how it's structured, okay? So I believe this covers everything the question is asking for. We did go through quite a bit, but hopefully you're able to keep track and understand how we're able to work through each value. So let's see how we did. So first of all, we have the electron configuration, which we were able to do, both the long and the shorthanded version, which is good. And then we have listed now 4 possible quantum numbers, okay? 3, 1, 0, plus 1/2. So they're referring to this one specifically, 3, 1, 0, plus 1/2. This is a possible set of 4 quantum numbers. If for some reason you were given like 3, 2, that is not a possible set because we do not have a D subshell in phosphorus, okay? So with that being said, this is correct. And we're free to move on to the next question. Okay, so question 2 for today. We have, why is the ozone molecule polar? So the thing you have to recognize is that ozone, although it's technically considered a molecular element because it's all composed of the same element, that doesn't mean that it's going to be perfectly balanced. And for example, like a good example is like O2. All right, that one is nonpolar because of the fact that when you draw it out, it's a double bond between them, and this is typically what oxygen looks like, so everything cancels out. But the ozone molecule, we're actually going to need to draw it out using the Lewis dot diagram and everything, just to be able to really visualize it, okay? So if we go to the periodic table, oxygen, all right, because it's O3, that's ozone. Oxygen is a 8th element, okay? So if we were to quickly do electron configuration, we start at helium, and the reason why I do this is because it's always good to verify that we have the right amount of valence electrons, and to understand electron configuration. We could just look at the columns and say, oh, it's column 16, oxygen has 6 valence electrons, but this is always a good way to really understand what you're doing. because we start from helium, and it'll be 2s2, and then oxygen is going to be 1, 2, 3, 4. That's 2p4. Okay, and you notice that the electron configuration also agrees that we have we have 6 valence electrons. So as the Lewis diagram states, you want to be able to use all those 6 from each oxygen. So we have to find a way to balance out 6 times 3, 18 electrons. Okay, so it doesn't matter which one we choose as the central atom because all of them are oxygen. So we're going to have oxygen here. We're going to start with just a single bond on each side. Okay, then we have the other 2 oxygens. All right, so now with it being said, oxygen contributes 6. So right now it's sharing 1 of the 2 on this side, which we're referring to the right oxygen. Okay, so well, 1 of the 6. So then we need 2, 3, 4, 5, 6 there. This oxygen to the left, same thing. We need 2, 3, 4, 5, 6. And then the oxygen in the center is already sharing 2 of its 6. So it's going to be 2, 3, 4, 5. Just making sure that I counted right. Yep. 1, 2, 3, 4, 5, 6. Oh, I started counting wrong. It's going to be 2, 3. Why did I do that again? It's going to be 3, 4, 5, 6. So this oxygen is content, okay? But what it could do, because as you can see, these oxygens have these radicals, these lone electrons, there has to be a way to kind of figure out how to balance it. So the best thing oxygen can do, really in this case, would be to specifically give one side that one of his extra ones, and then use the other electron to form a double bond with the other oxygen. The reason being is that if you notice, we still keep track of the same amount of electrons, but now oxygen still gets to keep its octet rule, and also at the same time it also gets to satisfy the other oxygens around it. So what we have now is oxygen in the middle, a double bond to the right, just because I chose it there, okay, and then we have oxygen to the other side with a single bond, but we have 1, 2, 3, 4, 5, 6. So if you count it out, actually, you will see that we still have 18 electrons in there. So just to be able to signify which is the one we change, we're going to put a red here, okay, because that's the double bond there, and we're going to put the red here, okay, because that way it shows all the things that kind of quote unquote moved around. So if we counted, we have 2, 4, 6, 8, 10, 12, 14. I think I'm missing. Oh, in the center, yes. 14, 16, and these will be still our 18. Just down here to mimic what we had up there. So exactly, that will be the Lewis structure for oxygen. And we can actually verify this through the electron number. So for the center oxygen, we have typically likes to have 6, okay, and it's going to be subtracted by how many does it have by itself right now? Only 2 electrons, and it's sharing around itself 6. So that's 2 plus 6 over 2, which is 3. That's 5. So this oxygen is plus 1, which makes sense. It's doing more than it should. And you notice that because we have a plus 1 and ozone is a neutral molecule, you're going to have one of the oxygens be a minus 1. Okay? So for the oxygen to the right, okay, it's going to be 6, and it has 4 by itself, and it's sharing 4. So perfect, that equals 0. So right now we have this as a plus 1, okay? And now for the last one, the one to the left, 6 minus, it actually has 6 electrons by itself, and it's only sharing 2. So 6 plus 1 is 7. So this would be the minus 1 right there. So this is where that negative charge is. So in total, it does make for a neutral molecule, but you can see how the oxygen in the middle is kind of doing more than it needs to, just to be able to keep the octet rule and keep the oxygens around it satisfied. So with all that being said, we now see that the structure for oxygen, if we drew it out, okay, would be like that. Just gonna do that. This would be the structure for ozone, okay? And right away, actually, this will actually tell you whether it's polar or not. When you have a an unaccounted for lone pair in the central atom, that lone pair also exerts its own force, its own electronegativity, its own pull. It's literally like a negative charge just concentrated there. So that is what's going to influence the pull of oxygen, because now it's no longer balanced. Okay, it has two types of bonds on each side, but then also has a lone pair. But with that being said, though, if we count all three to figure out the electron geometry, this electron geometry number is 3, okay, which is trigonal planar. That is the electron geometry, and this all ties into why it's a polar molecule, okay? And then if you want to do the molecular geometry, okay, we have 2 bonds. We don't count what type of bond it is, we just know that it's 2 bonds, and we have 1 lone pair. So 2 bonds, 1 lone pair. You'll see that it's actually bent. The shape is bent, and the reason why it's bent is because of the lone pair having its own field and pull, okay? As we check the Vesper theory here, 3 trigonal planar, you'll see exactly it's bent, and it kind of looks like water, like H2O. That would be kind of what it looks like. But exactly, this is what we're dealing with here in regards to the shape. Hopefully you can see the mouse hover over it. If not, I wish I could highlight it. There we go. This is the shape we're dealing with. And with all that being said, because it's bent, it already has an uneven distribution of things pulling the oxygen atom in the center, which is why it's a polar molecule, okay? And to go beyond that, just making sure that I've covered everything. Oh yeah, in regards to this, last thing you need to know, which doesn't really affect the fact that it's polar, it's still going to be polar, but ozone experienced resonance. As you can tell, the double bond could have been on either side, where it's shared like that. Okay, and that's how you signify typically like resonance structures. But exactly, this is what you'd get. Kind of something that looks like that, because it actually forms a resonance between the other oxygens, because that double bond could have been on the, that would be another resonance structure. I could have drawn it like this. It's still ozone, it's just a different type of resonance structure. Hence why it kind of looks like that, where the electrons are given more space to roam around, adding to its stability, which is why ozone can exist, even though we're dealing with the fact that 1 oxygen is a positive and 1 oxygen is a negative. So with that, they explain the Lewis structure, and because it has that lone pair and the uneven distribution, exactly, this causes dipole movement, and especially because that lone pair is really doing, I guess, what lone pairs do. It's no longer balanced because the lone pair doesn't have anything to counteract that. And exactly, you're also dealing with a single versus a double bond. So the whole, I guess, molecule is, yeah, uneven distributed, which is why this is considered a polar molecule. So with that being said, let's move on to question 3. What are the intermolecular forces present in each? Okay, we have H2O, He, CH3, Cl, and Co. Okay, so let's first list out the intermolecular forces. We have London dispersion, which is something that everything has, okay? So right now I'm just going to actually answer that part, and we're going to say all, okay? We have dipole-dipole, okay? which is going to be also, well, actually we don't know yet, we're just going to leave it as that. We have, sorry, I'm blanking out a little bit. We also have hydrogen bonds. Okay, and as the last one, we kind of just list ionic there, because that does play a role in intermolecular forces. With that being said, though, let's now talk about these. Okay, so let's start with dipole, because as I said, London dispersion, everything has London dispersion forces. It's like the basic force that just kind of like, if you think of these atoms as planets, when they pass by, they're always kind of exerting that little, I guess, gravitational force towards each other. It's almost negligible, but it is a force included there. Okay, now dipole bonds specifically refer to your periodic table, your electronegativity. So, with that being said, H2O, okay, we draw like that to show that hydrogen's bond with oxygen. So we want to know the electronegativity difference between hydrogen and oxygen. Okay, so it's going to be electronegativity, where is that number? 3.44 for oxygen and 2.20 for hydrogen. Okay, so that's going to be 1.24. And if you recall, at least from your notes, the dipole interactions, okay, have a range 0. So anything less than 0.4, that's going to be a nonpolar bond. Okay, nonpolar covalent bond. Anything between 0.4 to 1.6, that's a polar covalent bond. Okay, and anything greater than 2.0, okay, that's going to be an ionic bond. But more specifically, anything that has a metal and a non-metal bond together is typically going to be in an ionic bond. Okay, and so that range from 1.6 to 2.0, if it's a metal and a non-metal, it counts as ionic bond. But if it's still two non-metals, no matter how big the difference is, it's still going to be considered a polar bond. Okay, so with that being said, H2O 1.24, helium is a molecule by itself, so it literally cannot exert a dipole because there's no other molecule with it, so this one cannot have that force. CH3Cl, which does look like this, the one we focus on actually is going to be the bond between the carbon and the chlorine, because if you did the carbon and hydrogen, just as a context so you're not a little lost, we have carbon has 2.55 and hydrogen has 2.20. So it is a type of bond still, but it's actually the difference is 0.35. So it's actually a non-polar covalent bond, which is why we don't count it, because that's not going to exert a dipole-dipole interaction, because there's not really any preference the electrons have on which side they want to be on. There's no positive or negative ends. But carbon and chlorine, okay, chlorine has electronegativity of 3.16, and carbon has 2.55. So that's going to be a 0.61 difference, which in these numbers is significant, because that means that carbon and chlorine exert enough to where they actually form a dipole-dipole bond. Okay, so with that being said, this one checks out, this one checks out, and now carbon oxygen, okay, carbon monoxide, we have oxygen has 3.44 minus 2.55, we have 0.89, okay, something like this. I forget how carbon monoxide will bond, but yes. So with that being said, I'm just gonna write there because I don't know how it bonds, but the difference we know is 0.89, which checks out. So dipole-dipole interactions will be H2O CH3Cl and CO. And then hydrogen bonds. This one you have to memorize, unfortunately. There's 3 types, okay? There's hydrogen, There's hydrogen bonded with fluorine, hydrogen bonded with nitrogen, and as you maybe guessed based on your previous notes, hydrogen bonded with oxygen. So water molecules actually are a good example of hydrogen bonds. And looking at the rest, we have no other hydrogen bonds present, okay? So H2O will be the only one with hydrogen bonds. And then ionic bonds, that's when you specifically have a metal and a nonmetal. And when you look at all these, everything here listed is a nonmetal, so that's none. And the forces go like that, aka hydrogen bonds are, ionic bonds are the strongest, but the ones present, the H2O molecule probably the strongest one, and then followed by, we can't really say between CH3Cl and CO, but we do know that they do exert dipole-dipole, and then London dispersion. So as you can see, typically when you go down to the strength, you would notice that water, if it has hydrogen bonds, it most likely has dipole-dipole, and it obviously has London dispersion because London dispersion is always there. So that is how you would solve that question there. H2O, yep, dipole-dipole interaction, specifically hydrogen bonding, exactly. Helium only has London dispersion force, as we noted. CH3Cl, this is actually just going to be a dipole-dipole interaction, not an ion dipole interaction, just because of, like, in terms of, I guess, dissociation, no, you would still have just dipole-dipole interaction. CH3Cl likes to just, even though it forms those ends of positive and negative, the negative being on the chlorine, it's still just going to be dipole-dipole. And carbon monoxide, that one is also dipole-dipole interaction, okay? So let me see here, occurs when an ion encourages a polar molecule. I do not see, in this case, that we're going to be dealing with an ion dipole interaction because of the fact that we don't have any metals. So I'm going to say this is partially correct, but CH3Cl is just going to be dipole-dipole. CH3Cl is just dipole-dipole. Okay? If we were dealing with like NaCl, that would make sense. Or like if they were saying that CH3Cl, if it was poured in like a salt solution, which does have NaCl in it, then it would be experiencing that ion dipole interaction because the ions specifically from sodium would be reacting with the dipoles formed by the CH3Cl. But that would be a lot of assumptions made. It doesn't say any solutions submerged in. So as the molecule interacting with itself, so interacting with other CH3Cls, is just going to be dipole-dipole, okay? So I'm still going to say it's correct because for the rest of them, it does explain it. But this is the type of sheet you're looking for here, okay? So now question 4. What is the charge of nitric acid? So the first thing here is you have to understand what nitric acid is, okay? So with that being said, okay, we have nitric acid being, we know there's a hydrogen because acids need to have that proton. And what does nitric in this case mean? So I'm not sure if you're familiar with the ion nitrate, okay? Because 8 nitrate with the 8 ending, when you add the hydrogen to it, or hydrogens, it goes from 8 to ic. Okay, the 8 gets dropped, the ATE, and it turns into ic acid. So if you want to go backwards, if we have nitric acid, and we took away the hydrogens, okay, we have nitrate, okay? That is what we want to go back to, okay? And we need to know what the nitrate ion is. So the nitrate ion, this one is unfortunately one of the things you have to memorize. but I do kind of have a strange way of knowing whether I have it right or not. Nitrate stands from nitrogen and a certain amount of oxygens, okay? And I'm going to put NO3 because nitrate, specifically the ion, has a charge of -1. How do I know whether this is correct? What I like to do personally is assign the electron numbers with them. So oxygen, it likes to have the electron number of 2, and so because there's 3 of them, it's going to be 6. Nitrogen, okay, and think of these ions specifically always being negative. So I don't assign any positive or negative signs to the numbers just yet. But nitrogen, okay, it's going to be in the 15th column, so it's going to have 5 valence electrons. And so the only way for this to work for the -1, which is why I don't assign any negative values or positive yet, it has to be that the 6 is negative, okay, and the 5 was positive. But I like to do it like this because if my numbers weren't matching to where I could not even whether add or subtract to get to the -1 that I wanted, then I know that I have the wrong amount of oxygens. Because nitrate is the one with the oxygens that the charge makes sense. That's how I like to break it down and memorize it, because there's also things like nitrate. There's also like nitrite, for example, which is NO2, and it still has a -1 charge. So it just things like that makes it a little bit tricky, but I find that by memorizing the 8s, you have a little bit of an easier time with the ites because it's just subtracting oxygen. So with that being said, hydrogens typically, well, protons have a positive charge. Nitrate, as we've shown here, has a just negative charge. So nitric acid would be HNO3, okay? This is nitric acid. Now they're asking for the charge, okay? So with that being said, the charge of nitric acid itself, because the positive and negative canceled out, is neutral. That right there is the answer to this question, because acids are going to be neutral. If you're referring to their conjugate base, which is what we did actually earlier here, that conjugate base has a charge of -1. Like things like acetates, like because I'm thinking more like, you know, like acetic acid, okay? That one, its conjugate base is called acetate, okay? And acetate has a charge of -1 because now you've taken away one acid. A better example would be like H3PO4, which is phosphoric acid, okay? And this has still neutral charge. You take away one hydrogen, okay, H2PO4, and now we're dealing with dihydrogen phosphate, okay, which is -1. Take away another hydrogen, and now we're dealing with hydrogen phosphate, which is -2. And if you take away that last hydrogen, we have this phosphate ion, okay, which could be 3-, okay, 1-, 2-, 3-. That is what we're dealing with here in regards to the charges. But exactly, when you start with the one filled to the max with hydrogens, which is what H3 is for phosphate, that is when you have a neutral charge, okay? So with that being said, formal charge is valence electrons minus the change in the lone pairs versus the electrons in bond. So what they did actually in terms of finding their formal charge is what we've been doing. I've been calling the wrong thing, sorry. But we actually have been finding the formal charge, which is when we, for example, like when they drew the Lewis dot diagram, the goal here is to make sure that all the charges, so let's just do that, oxygen, double bond here, single bond here, and then the hydrogen there. Okay, so if we actually went and did the formal charges, which is what we have been doing, but the way to find formal charge is we get the molecule in the center, okay, so the nitrogen, and then we say that it typically likes to have 5 because that's 5 valence electrons. Then we subtract the amount of electrons it has by itself, which is none, plus the amount of electrons it's sharing, which is 8. We have to divide that by 2 because it's sharing it. So you end up with a +1, okay? And because you have a +1, you know that because nitric acid is a neutral compound, you need to have a -1 somewhere. But this is what they mean by formal charge. And then oxygen, the one here to the right, okay, we're going to do, it's going to be 6, because that's what oxygen likes to have in terms of valence electrons. It actually has 6 electrons by itself, plus it's sharing 1 with nitrogen. So it's actually going to be, that's where your -1 is. This is where your negative charge is held. Because if you did the math for the rest of the oxygens, actually, just going to actually add the other electrons. But if you did the rest of the math, you would see that the oxygen to the left, where the hydrogen is 6, minus, it only has 4 by itself and is sharing 4. So that does equal 0. The oxygen up top, same thing actually. It has 6. It's, well, valence electrons is 6. It has 4 by itself and is sharing 4. And the hydrogen, just to make sure, typically has 1, doesn't have any, and is sharing 2. And that equals 0 as well. So all the math checks out to where actually you know where your positive charge is held and your negative charge is held, to where the whole compound itself, nitric acid, is neutral. Just as how the picture has shown, okay? But the way I just reasoned it out is because exactly acids, most of the time they're going to be neutral, okay? Because then when you start dealing with things like for example, like H2PO4, technically can still have acidic properties where the hydrogen dissociates to HPO4, but typically you wouldn't see it called acid if I attach a sodium to it. So if I had NaH2PO4, this is known as sodium, well, monosodium phosphate, okay? It's no longer called monosodium phosphoric acid or anything. It's just called monosodium phosphate. And that is because of the sodium attached to it. It can still do acidic things, but when you have acid in the name, think of it as most likely it's going to be a completely neutral molecule. Okay, so this is correct. And just so I remember, formal charge is what it's called, where you list these out and you solve it like that. So now we're dealing with question number 5. What are the complete Lewis structure, including valence electrons, of the following compounds? So let's start. So Lewis structure for A, F, H, B, H, O, H, and C, O, N, H. So for this, what we actually do, they've given us quite a big hint because they at least show us how it's bonded, but we have to always make sure that we're counting the right things. So fluorine, okay, is on column 17, but even using the electron configuration, starting from helium, it's 2s2, 2p5, okay? That also supports that because it's on column 17, it has 7, 2 in the 5 valence electrons. Hydrogen, on the other hand, is just 1s1 because it's the first element, and also it's on the first column, so it has 1 valence electron. So in total, we want this Lewis structure to have 8 electrons. So 8 electrons. So to draw that, it doesn't really matter which one you start with, there's only 2. Okay, so we have the F, and it's sharing a bond with hydrogen. So hydrogen has now used up 1 of its 1 electron, so it's good. But fluorine has only used 1 of its 7. So it has 2, 3, 4, 5, 6, 7. And as you see, this fits perfectly the octet rule for fluorine. Fluorine is completely satisfied as well. Hydrogen is done. This right here is your Lewis structure for hydrofluoric acid, okay, FH. Now HOH, we've established that hydrogen is just 1s1, but oxygen is right before fluorine, so using that support as well, 2p4, we can actually verify that oxygen does indeed have just sorry, I'm blanking out a little bit, that we can verify that oxygen just have indeed just 6 electrons. So there's 6 and hydrogen has 1, but there's 2 of them. So in total we have 2 plus 6. So we also need 8 electrons. So for this one, because hydrogen is the only unique one here, we put it in the center. And we're going to put it as this sharing 1 bond each with the hydrogens to the left and the right. Okay. So now hydrogen is shared 1 of its 1, so it's complete. But oxygen, so far, because it's in the center, has shared 2 of its 6. So then we have 3, 4, 5, 6. So this also, oxygen is now complete as octet rule. It's completely satisfied. This would be your Lewis structure. And even to verify that as well, we're actually going to get its trying to remember what that was called. We just talked about it briefly. Should have written a note down. But we're actually going to get the number in terms of the, I guess, to see where the positive and the negative charge are. It's, I guess, theoretical charge. Let's just call it that for now. We have fluorine, okay? It's, like we said, 7 valence electrons. And right now, it has 6 by itself. So it's going to be 7 minus 6. And it's sharing 2. And because it's sharing from divide, and that does equal 0, so fluorine has that theoretical charge of 0. Hydrogen, okay, is going to be 1, and it has 0 by itself, and it's going to be sharing 2, so that also equals 0. We're going to flip it over here. We know how the hydrogen works because it's the same thing. Okay, so still a theoretical charge of 0, which is great. And oxygen is going to be 6 now, minus, it has 4 by itself, and it's sharing 4 electrons. So with that being said, this also equals to 0 for the theoretical charge. So everything's looking good, because we want to note that because these molecules are neutral, we want to have that theoretical charge as neutral as well, which is what we got. So now ONH, okay, written like this, so thankfully it shows which one is in the center. Typically what happens is that the center molecule is the one that has usually the most space, indicated by being like around like carbon, nitrogen, because those ones have 4 I guess unpaired electrons. Nitrogen has 3 unpaired electrons. So let's just actually break that down. Oxygen, as we discussed, is going to be this 2s2 2p4. That means it has 6 valence electrons, also supported by it being on column 16. Nitrogen is going to be right before it. Okay, so it's 2s2 2p3, also supporting that it has 5 valence electrons, and the hydrogen is just that 1s1, okay, which is going to be 1. So now we have 6 plus 5 plus 1. In total, we need to find a way to share 12. 12 electrons need to be shared. So as it's shown here, nitrogen is in the middle. Okay, we're going to start with just a single bond on each side. We have the hydrogen and we have the oxygen. Okay, so with that being said, hydrogen is complete. Oxygen still needs 5 of the 6 because it's only sharing 1 of them. So it goes 2, 3, 4, 5, 6. So we're done with that. And now nitrogen is right now sharing 2 of its 5. So it needs 3, 4, 5. So with this being said, actually I'll write it down here. I like doing a certain thing. As you notice, we have 1 lone electron on each one, which is why we can then get the electrons to kind of move over here to form a bond with each other. That way, they're both satisfied, still fill the octet rule, and can move on with their lives. So we have now nitrogen, okay, with the hydrogen, and as shown in that picture above where it shows that double bond, this is why when it comes to a Lewis dot diagram, So we have the oxygen, okay, and we have it just like that, and the nitrogen is just like that. And I'm going to make these red to signify where those electrons went. So now this is our Lewis structure for ONH. Don't really know the name of this off the top of my head, but the point being is that when we actually check the numbers now, the theoretical charge numbers, okay, we have hydrogen is still good, 1 minus 0 plus 2 over 2, because that's all it's sharing. Oxygen, okay, it's going to be now 6 minus, it's still going to actually be, has 4 by itself, and it's sharing 4 of them with nitrogen, so it's still going to be 0. And nitrogen, okay, is going to be 5 minus, it has 2 by itself, and it's sharing 6 with the surroundings, which is perfect, because that's exactly what we want. So now we'll be able to see that these are all the Lewis structures with their theoretical charges. All of them are 0 because there's no positive or negative charge, because overall we have a neutral molecule for each one. And there you go. We have the Lewis structure. So we have, yep, I like to draw my bonds even as just the electron dots. So that's why it looks a little bit different. Exactly. We have this as well for Lewis structure. And then we have that. So with this being said, this is correct. And we're able to even support why these molecules are going to be theoretically, well, they are, have no charge, because the theoretical charges were all 0. So now let's move on to the next question. Which statement best describes O3? Okay, so that would be your oxygen, okay, and they're wondering which statement best describes it, okay, and that's very strange because they have, well, I guess that's a separate question after, but each atom in ozone is connected to an atom by a bond having a bond order of 1.5. Wow. The double bond in ozone switches back and forth between the 2 outer oxygen atoms. An ozone molecule contains 1 single bond and 1 double bond. Okay. So, with this being said, the way to tackle this question is to first understand what ozone is by drawing this Lewis dot diagram, okay? So, oxygen, all right, is the 8th element, okay? So, using both just the column it's in and the electron configuration, which is something I like to do in the shorthand notation, we can actually see that oxygen has 6 valence electrons, being the 8th element. Specifically on the things on the 16th column typically have 6 valence electrons, and also can be supported by the electron configuration. But there's 3 of them, so we need to account for 18 electrons. Okay, so with that being said, we have 1 oxygen in the center at least, sharing 1 bond on each side with another oxygen. And because oxygen comes with 6, okay, this oxygen on the right and the left need to fill at least that part up. So it's going to have 2, 3, 4, 5, 6, okay, and then the other oxygen, the same thing, 2, 3, 4, 5, 6, all right, and then the oxygen in the middle is sharing right now 2 of its 6, so 3, 4, 5, 6. So the oxygen in the middle is actually completely satisfied, but this setup doesn't work because the oxygen on the outside have these radical lonely electrons. So what's actually going to happen here is that no, these 2 do not bond with each other from across. You don't end up with like a triangle for ozone. That is actually not how it's going to work, unfortunately. I've thought about that, and no, it's not the case, unfortunately. So what actually happens here is that this is going to split and form a double bond with one side of the oxygen. This is all theoretical, by the way. You'll see later it's not actually a double bond, but this is what happens on this side, and on this side, this oxygen just takes it. Because the reason why it cannot be another double bond is because then the oxygen here in the middle would break its octet rule. It would have 2 double bonds on each side, and also it would have a lone pair. So that's 5 things in total it'd be quote unquote attached to. And that's not, well, not 5 things. It would be 10 instead of 8 electrons that it would have surrounding it, which is not what it wants. So with that being said, if we redrew this, okay, we'd have O, okay, and this is what we get, okay? So it still fills its octet rule for the central oxygen, and each oxygen on the side has filled its octet rule as well. And the theoretical charge for each oxygen, okay, would be starting from the right, and we're going to go to the left from there. So it's going to be 6, because that's its valence electrons, minus it has 4 electrons by itself, and it's sharing 4. So you divide that by 2. So 4 plus 2, that's equals 0. The oxygen in the center, okay, it actually only has 2, and it's sharing 6. So that's going to have a charge of +1. So this oxygen here has a charge of +1, which makes sense because the oxygen all the way to the left, okay, that one there, is going to be 6. It has 6 already by itself, and it's sharing only 2 of them. It's going to be -1, because 6 plus 1 is 7, and 6 minus 7 is -1. Okay. So now, with all this being said, though, we could have just answered the question saying that, oh, well, that means that ozone contains 1 single bond, 1 double bond. That would be technically incorrect, because now you have to factor in your resonance, okay? Another resonance structure for this, which I could have equally drawn as well, which is not the same thing, would be this. You may have said that, wait, you just flipped it over, but remember that these are all separate separate atoms with their own identities. What I've done is that I've said that this oxygen on the left receives the double bond instead, and this oxygen on the right has now the negative charge, and this one would actually be -1 here, still positive in the center. But now we have 2 different types of resonance structures. So what you see here is that typically what's going to happen to get the maximum stability is that the electrons actually will be shared, to where instead of you having a single and a double bond, you would actually technically have it would kind of look like that, okay, to where one of the bonds is like dashed out, because it's not that the single double bond or like the double bond is switching back and forth. You actually have a complete structure where you kind of have 1.5 bonds theoretically, okay? In this case, it would be like a pi bond and a sigma, or is it sigma pi? I think it's sigma first, then pi after, kind of like that. This is what you'll be dealing with, where they're sharing that pi bond-ish to where it forms that resonance structure. Point being is that here, each oxygen has more so of a 1.5 bond, okay? Not that it's 2 on 1 and it's bouncing between, is that the whole structure, the electrons are moving through the whole thing, kind of creating that 1.5 bonds on each side. So with that all being said, the most correct statement is here. Each atom in ozone is connected to the other atom by a bond having the bond order 1.5. This is the most correct statement. That's why the answer for this one is A, the first choice. Because a double bond, as I stated, is not switching back and forth. That's just when you represent the resonance structure. But you want to be able to get the whole picture of resonance. Because the resonance structures are just simply, I guess, possible extremes of when the electrons are moving about. But you know, you don't want to go for the extremes. You want to go for what's most probably going to happen, which is that the electrons are somewhere in between the 2 oxygens at the end. And because they're somewhere in between, we say that's around a 1.5 bond on each side. There could be a moment in time where it's like 1.7 on one side and 1.3 on the other, or really close to 2 on one side and really close to 1 on the other. with point being on average, it's going to be about 1.5. And the last one, ozone molecule contains one single bond and one double bond. As you've seen here as well, that is not the case. Okay, it's neither just a single and double bond, it's more like 1.5 bonds. So with that being said, the correct answer is the first one. It does not contain a single and double bond. It's kind of just a mixture. Okay, it's more so 1.5 bond. So this is correct. Okay, so let's move on now to question number 7. Hope I counted it right. Yep. Is SCl2 a polar or a non-polar molecule? So first we have to figure out what S is. Okay, so S is sulfur. So is SCl2 polar or non-polar? Okay, so with that being said, to find out whether it's polar or non-polar, we need to do our Lewis dot diagram. And so we first need to figure out how many each element contributes. Sulfur is going to be on the 16th column. So in terms of the valence electrons, we have 6. You can also show this by electron configuration. And the reason why I keep stressing this is because you do have to get familiar with electron configuration, especially as you go further in chemistry. That is a question that can commonly pop up. So we have, at least in the shorthanded noble gas notation, we'll start with neon. Okay, and then we go over to 3s2 because it's on the third row, and 3p4. And you'll notice here that even this supports that sulfur has 6. And if we treat chlorine the same way, because chlorine comes right after it, is that neon 3s2 3p5, which also supports that chlorine has 7. Okay, but there's 2 chlorines, so chlorines actually, well, the chlorines together contributing 14. So 6 plus 14, you want 20 electrons accounted for. Okay, so put the sulfur in the middle because that's the only different one, and then we put that as sharing. Now just a single bond on each side with the chlorines. So starting with the chlorines are right now sharing 1 of its 7. So it's going to be 2, 3, 4, 5, 6, 7. Amazing. Octet satisfied. 2, 3, 4, 5, 6, 7. Awesome. Another octet satisfied. Now sulfur is already sharing 2 of its 6. So it's going to be 3, 4, 5, 6. Great. Another octet satisfied. And now to make sure we have the right number, we're actually going to quickly do the theoretical charge of each one. So sulfur in the center is going to typically have 6 as valence electrons. Okay, so with that being said, you would subtract the amount of electrons it has by itself, which is 4, and that's added together with the electrons it's sharing, which is also 4. You have to divide that by 2 though, because this is sharing. So then we have 6 minus 6, which is 0, which is perfect. So chlorine should also have a charge of 0, hopefully. But this one, 7 valence electrons, it has 6 by itself, and it's sharing only 2. So 6 plus 1 is 7. So we do indeed get that 0. So we're good. This is the Lewis dot diagram for SCl2. Now it's asking if it's polar or non-polar. The big red flags you see here are these electrons, okay? Because this goes now into its molecular shape. So first, if you want to find out the electron pair geometry, we first need to, I guess, count how many things it has surrounding it. And a lone pair counts as 1, okay? So we have 2 lone pairs and 2 bonds, so it has electron pair geometry, or the number 4, which is tetrahedral. Okay? But, as we said, so this would be the electron geometry. So, but the molecular geometry accounts specifically which of them are bonds and which of them are just lone pairs. So we have a 2-2 split, making this shape actually bent. Because why is it bent? You have the sulfur in the middle, the chlorines, okay, and just specifically talking about the sulfur in the center, okay, the electrons are what's setting it off balance. They don't even cancel each other out technically, because although the electrons are kind of pulling each way here, the chlorines are slacking off in a sense, okay? So it kind of has a net charge going this way, because although the electrons will cancel each other out left and right, the upwards momentum is what's going to set the chlorines, I guess, off to where sulfur is now a polar molecule. So that's the thing you have to recognize, kind of like with H2O, where it's polar as well. You look at the Vesper theory, it's tetrahedral, but it's actually bent for its molecular geometry, okay? And this type of molecule you get right here at the end, okay? And because you have that, it's actually going to be polar. You can see there that there isn't even distribution. Because of the lone pairs, it's an uneven distribution, which is why I can say with confidence that SCl2 is a polar molecule, okay? It's not nonpolar, even though it looks like that based on its Lewis dot diagram. The electrons there, you have to make sure you draw it out, look at its geometry, because you'll see there that it's actually not nonpolar because of the fact that it has like a bent shape, okay? So exactly, as you see here, it has an angular molecular geometry, although it's symmetrical in respect to its, I guess, Lewis dot diagram, and that vertical axis, the horizontal axis, or I guess I said it backwards. In respect to the horizontal axis is kind of symmetrical. The vertical axis, though, is asymmetrical. Okay. So that being said, it is indeed polar, and this is correct. So let's move on to question 8 now. Draw the Lewis structures for, wow, that's a lot of them. Draw Lewis for TeCl4, ICl5, PCl5, KrCl4, and XeCl2. Okay, which exhibits a bond angle that's approximately 120. Around 120 degrees. Which compound exhibits D2sp3? I think they wrote that wrong. They want which exhibits sp3d2 hybridization, and which, wow, this is a big question, which have a square planar, okay, and which are polar. So, wow, we're gonna be here for a little bit, but that's perfectly fine. Okay, so we're gonna start off with TeCl4. Okay, so Te is tellurium, which is all the way down here. Okay, and we have chlorine. So TeCl4. We're still gonna go over, you know, things like the electron, electron configuration and such, in regards to like how many electrons they contribute. You know what? Actually, for this question, considering that we have quite a bit of ground to cover, we're gonna skip that. We're just gonna go simply by the where it's located on the periodic table. So it's the 16th column for tellurium, so it provides 6 electrons. Chlorine's on the 17th column, so it has 7 electrons. There's 4 of chlorine, so it's going to be 7 times 4, and then plus that 6, we need to account for 34 electrons. So let's start out by drawing it. Okay, so tellurium, it's in the middle. Give yourself enough space. Okay. The chlorine, it's going to be at each end. And tellurium, just letting you know right now, is going to be one of those that breaks the octet rules. But first, let's fill out the chlorines at the end. It's sharing one of its 7, so 2, 3, 4, 5, 6, 7. Perfect octet filled. Same thing here. Another octet. 4, 5, 6, 7. Another octet. 2, 3, 4, 5, 6. Another octet. So now tellurium is so far only sharing 4 of its 6. So it's going to have 5, 6 right there. So tellurium actually technically has 5 things bonded to it, okay? Whew. So that's for tellurium. We're going to stop there because we're going to actually draw everything else before we get into in terms of the electron geometry of each one, okay? And we have, I hope I wrote this right, ICL 5. Is it ICL 5 or ICL 3? ICL 5, okay? So that's what we have for tellurium, okay? ICL 5, okay, is going to be ICL 5. Chlorine still offers 7, and iodine actually offers 7, so we need to account for 35 electrons, okay? So kind of following the same for tellurium, we have iodine in the center, okay? And we're going to have each side having a bond, but there's 5 chlorines, so this is how I kind of have that other one in red for tellurium. The 5th one, because iodine also doesn't care about the octet rule, is going to be like that. Whoops, so it's not 35. Definitely did the math wrong. It's going to be 7 times 6. Did not account for, I thought we're still dealing with 4 chlorines, so it's going to be actually 42 electrons. So we're going to have quite a bit we got to count through, okay? So for tellurium, before I actually go ahead, I'm going to make sure we actually have 34, okay? So there's 8 on each chlorine, so 8, 8, 8, 8. So that's 32, and then 2 more on that tellurium, which is 34. Perfect. So with that being said, let's fill out the octet for each chlorine, because it is sharing 1 of its 7, so the other 7 are going to just be filled in. Okay. All right, and then for this last chlorine we have, it's going to be a little bit of a squeeze here, like that. And then iodine is actually sharing right now 5 of its 7. So we're going to have, again, 6, 7. So with that being said, we have 8 times 5, which is going to be 40. Okay, plus 2 more, 42. Perfect. Then we have PCl5. Okay, so we have PCl5, and just to make sure that's actually what we're dealing with. Yep, perfect. So we have another one in the middle, phosphorus. Okay, and we have sharing 1 each. Maybe I should give myself more space. Actually, I'm gonna actually move this all the way to this side, because I'm gonna be writing down the shape and everything right under it. Okay, so just put it like that. All right, so with that being said, we have a chlorine here, a chlorine there, chlorine here, and then they said there's a 5th one, so gonna be a little bit of squeeze, chlorine there. So the same octet rules being filled. So 1, 2, 3, 4, 5, 6 of the 7, same here, and the same here, and then the same here, and then for that extra chlorine, same thing. All right, and kind of skipped ahead. PCl5, phosphorus can only donate 5 because it's on the 15th column. Chlorine still is 7, and there's 5 of them, so 7 times 5 is 35, plus 5, 40. So we have 40 electrons, and if we actually go around 8 times 5, because each chlorine is the octet rule, we do get 40. So this is perfect. Now for the next one, we have krypton Cl4. Okay, so, ooh, wow, yeah. So this can't run out of steam here. Krypton Cl4. Okay, so Kr. Okay, has those bonds there. I'm just making sure, just have to double check that we actually have the right amount. Okay, so we have now, okay, chlorine, 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 okay, and then we're gonna now add the extra electrons. Let's start with krypton in the middle. It's right now sharing 4 of its 8, so 5, 6, 7, 8. Okay, so krypton is done. Krypton Cl4, it's 8 being donated because it's on the 18th column. Chlorine is still 7 times 4, so 7 times 4 plus 8. We have 36 we need to account for. Okay, so with that being said, we have each chlorine has 1 of its 7 electrons being shared. So now it's 2, 3, 4, 5, 6, 7. Same for each chlorine. Okay, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, so with that being said, 8 times 4 is 32, plus 4 more on the krypton, 36. So we're good there. Now for the last one, xenon Cl2. Okay, so maybe I should actually move these a little bit because we want them to kind of match where they're hovering over. So this is krypton. This is PCl5. This is ICl5. Okay. So the last one is xenon Cl2. Okay. And that's going to be xenon in the middle again. Xenon has 8 electrons because it's on the 18th column. Chlorine still has 7. So 7 times 2 plus 8. 22 electrons we need to deal with. So we have just 2. Thankfully it's a lot smaller. Excuse me, sorry about that. Alright, so now we have the chlorines on each side. And then fill out the octet. It's only sharing 2 of its 7. I mean 1 of its 7. So 2, 3, 4, 5, 6, 7. Xenon is right now sharing 2 of its 8. So it needs 3, 4, 5, 6, 7, 8. So that's xenon there. It also breaks the octet rule in this case. So with that all being said, this is the behemoth of Lewis dot diagrams we have. So now these questions, which exhibit a bond angle that is 120 degrees, around there. So for this, first you have to actually know the electron geometry shape, okay? Alright, so for this, to find the electron geometry, we first need to figure out what the electron pair geometry number is, okay? The hybridization, okay? So, and we figure that out by seeing the amount of things it's quote unquote attached to. It's attached to 1 single bond, another single bond, 3 single bonds, 4 single bonds, and 1 lone pair. But in total, that's going to be hybridization of 5, okay? And if you have a hybridization of 5, that is sp3, because 1, 2, 3, 4, 5. sp3d, that is your hybridization. Okay, because S counts as 1, P 1 through 3 count as, so sp would be a hybridization of 2, which would look like that. That's an sp hybridization. Like a perfect example is carbon dioxide. That's a sp2. I mean, that's an sp. A good example of sp2 would be NH3. No, it won't. Sorry. A good example of sp2 would be like boron. Yes, boron, because each hydrogen takes 1. That is a good example of sp3. I mean, I keep skipping. sp2 sp3 is like CH4. Okay, that's a good example of sp3. And then because this has a fifth one, it's sp3d. Now for iodine, we're going to treat the same. We have 1, 2, 3, 4 bonds, but 2 lone pairs instead of 1. So this one has actually a hybridization number of 6, which is sp3d2. Okay, which is, you remember, that's one of the questions they were asking, which exhibits that. Phosphorus, on the other hand, okay, is going to be, just to make sure, how did we do phosphorus? PCl5, and Tertium was just TCl4. So phosphorus actually also is going to be, if we note it, it's going to be 1, 2, 3, 4, 5. So 5 things as well. So it's going to be 5, which is, as we discussed, sp3d hybridization. Krypton, okay, is going to be 1, 2, 3, 4, 5, 6. So krypton is actually also showing off the 6 sp3d2 hybridization, and xenon, okay, is going to be, if we count them, the things attached to it, 1, 2, 3, 4, 5. So 3 lone pairs and 2 bonds. That's still going to be 5. So that's hybridization of sp3d. So far we've answered this question here, which exhibits sp3d2 hybridization, is going to be ICl5 and krypton Cl4. Okay, so now with that being said, the next questions depend on the actual electron and molecular geometry. So the electron geometry for this, because it's sp3d, is going to be, if I remember correctly, trigonal bipyramidal. And for 6, it's actually going to be octahedral. So this is going to be trigonal bipyramidal. Now remember, this is the electron geometry. It gets a little bit different when it comes to the molecular geometry, because molecular geometry actually accounts for whether the bonds are actually lone pairs or actual bonds, the things attached to it specifically. So this one's also going to be octahedral. Okay, again, trigonal bipyramidal. Okay, so now let's move on to molecular geometry. What is the ratio of bonds to actually lone pairs? It's 4 to 1. And I'm going to tell you honestly, I don't have that shape memorized, but let's just go right now, just listing out. Molecular geometry for this one is going to be 4 to 2. Okay, and this is going to be 4 to 1 as well. All right, no, actually, sorry, I miscounted. It's just going to be actually 5, because, you know, each chlorine is where the single bond is. So good news is that this one actually stays trigonal bipyramidal. Okay, because the shape name stays the same when you actually are completely full. This one here is going to be a ratio of 4 to 2. Okay, because it has 2 lone. Let me actually count again. This is not 4 to 2. I keep ignoring that chlorine. So it's actually 5 to 1. Okay, and this shape I don't know either, but I do know 4 to 2 specifically is actually going to be a square, planar. Okay, that's the shape we're dealing with there. And for this one, it has 3 advanced electrons, so it's going to be 2 to 3. Okay, and that shape I do not know. Actually, I think this is actually linear, but I may be wrong. We'll have to go back and fix that. But yes, these more fancier ones I'm not too familiar with, but the point being is that this is linear because if we drew it like this, okay, with xenon in the center, the electrons kind of surround it in its x-axis, and then we have the chlorines on each end. Okay, so kind of like if I were to draw out the shape, it would be like a circle and a line that goes through that circle. So kind of end up with looking like this pretty much. If you looked at it from this angle here, okay, it'd be a straight line down, straight line there, which is why it's a linear shape. These lone pairs cancel each other out in the x-axis, and the chlorines cancel it out in the y-axis. So this actually is a nonpolar molecule. Okay, so just to make sure, yep, trigonal bipyramidal, it's linear. The reason why this is square planar is because you have the krypton in the center, right? And then you're going to have the chlorines kind of in the I guess the x-axis part, okay, where it literally forms like a square. Don't know, I can't draw this line properly. There, okay, and the chlorines are here, and you have the two lone pairs that cancel each other out from the top and the bottom. So they kind of have like a sheet that looks like that, and the lone pairs kind of stick out like that. So if you looked at it from this angle, kind of similar to the one previously, you have also a nonpolar molecule because the x-axis cancels each other out and the y-axis cancels each other out as well. I probably signed that wrong. The x-axis cancels each other out and the y cancels each other as well. But yes, this is a square planar for krypton. And one of the questions actually asking that, which has a square planar, that would be this one here, this octahedral shape. So krypton, Cl4 will be the square planar. Phosphorus is also going to be nonpolar, but it's going to be pretty much trigonal bipyramidal, to where it's like you know, phosphorus in the center, and how do we draw this again? It's going to be like that, 1, 2, 3, 4, 5, okay, like that, and each one is going to be like the chlorine. So it's going to be quite similar to the you know, this one here, okay, where you have kind of like the chlorine circling about there and a line that goes through it. So if you looked at it directly, it'd be kind of like this. So they still do cancel out and everything. And each angle here, actually, as you see here, the three kind of splits. And I'll actually go over the angles for the other ones, but you see that these ones will actually be like 120 degrees. Okay, and then these will actually be 90-degree angles. Okay, because as you can see here, if we drew it like that, you can see the 90-degree clearly. This one, you can see the 90-degree clearly, and actually each chlorine between them is also 90 degrees. And if we went back to xenon, the electrons are what's having that kind of 120-degree angle, but we don't count the electrons. Okay, so all we have here is just really, because it's linear, it's 108 degrees. Okay, because the electrons, we don't really count them because it's not really a bond, so we don't really say that they have like a certain distance between them. So with that being said, right now only this one here, the PCl5, has that 120-degree bond that they were looking for so far. Okay, and now I'll fess up, these ones I don't know what shape they're expecting between 4-1 and 5-1. I'm pretty sure the 5-1 looks like, actually let me think of the 4-1 first. I'm pretty sure the 4-1 looks like if I were to draw it out, if I remember correctly. Don't know what the shape is called, but it's kind of like that. And these two kind of are squeezed together because the electron here is a bully. So we still have this, okay, what kind of looks like that. But the issue here is that, if I counted it correctly, the issue here is that because the electron, you know, it's kind of making sure that it's bullying them in a sense, it kind of pushes the chlorines further away from it because electrons exhibit, I guess, more of a harsher push. This bond right here would be less than 100 degrees, 120 degrees, but it's still going to be around it. So we can still actually count this as a 120-degree bond. But here, though, the same thing is that you would think that it's 90 degrees, right? But because that electron here is still exerting that bullying push, it's going to be something that's just less than 90 degrees, okay? That's usually how you signify it, because when it comes to these, whenever there's like an electron involved directly in there, unlike these two where the electrons cancel each other out, what happens here is that they exert their own kind of push towards everything else, literally, to where it kind of like squeezes everything. Now, with this being said, this one here, okay, would look kind of like this. Okay, so we have iodine, okay, and we're gonna have the, I guess, the planar part that would be planar theoretically. Then you have the electron, and like that. I'm pretty sure that would be how you draw it. Okay, so we still have, I guess, this shape here. We kind of have the square, and then, you know, if we drew it to the side, like that. But because the electron has that push up there, everything kind of squeezes in. So instead of it just being like perfect 90-degree angles, these ones here will still exhibit that 90-degree angle, because I guess they're kind of, we just say that everything here is kind of just less than 90 degrees. Okay, so that is the shapes I'm thinking so far. But let's actually see their name, which is why we have the Vesper sheet here and ready for us. So as you can see here, if we scroll all the way down, trigonal bipyramidal, a 4:1 ratio is a seesaw. Okay, and that is actually what we got. So we have, at least from what we drew. Okay, and 5:1 is a square pyramidal, which is, yeah, we got that too. Nice. So square pyramidal. 5, 0, okay, as you can see here, is still trigonal bipyramidal, which is what we got, and that's the shape we got. Okay, and 4, 2, if we go down here, square planar, which is also what we got. And now for the last one, 2, 3 is linear, which is also what we got. Perfect. Just was blanking out on the names for these. So now reviewing what the question was asking for, okay? Which exhibits a bond angle that is around 120 degrees. That will be the TeCl4, as you can see here, between these two chlorines, okay? Based on the seesaw, you can even see here an even better example. The two chlorines at the bottom, that's kind of around 120. And also, it would be PCl5, perfectly just around it. That would be what we have a whole 120 degrees between the chlorines in like the x-axis. So, which exhibits sp3d2 hybridization? That would be ICl5 and krypton Cl4, which have a square planar, specifically not square pyramidal, but square planar. That would be only krypton Cl4, because the other one is square pyramidal. As you can see the difference. Okay, and which are polar. Okay, as we discussed, so this one will be polar. Okay, so actually I'm going to highlight in green. Because of that, it's polar. This is also polar. So the first two are polar. TeCl4 and ICl5 are polar. Okay, this one is going to be non-polar because all the chlorines cancel out. This is non-polar because the electrons also cancel out. And this is non-polar because the electrons around it cancel out. Okay, so yes, that is all we have for this question, even though it was a lot. So it wasn't all we had. We had quite a bit. So let's go back to what this says. TeCl4, did we draw that correctly? Yes. Yes, for ICl5. Yep, just double checking. It's 5 and 1. Yep. PCl5, correct. KrCl4, correct as well. And XeCl2, that is also correct. So with this, we can just skip over that because we've already gone over it. But TCl4 has a square planar. No. ICl5, it's trigonal bipyramidal, and just to make sure I was looking at it correctly, 4-1 is seesaw. That is, I guess, the shape is what it's called. So that's incorrect. So this question is already leaning towards the incorrect. But ICL5 has square pyramidal, which is correct. PCL5 has trigonal bipyramidal, correct. Square planar, so that's actually what they mean here. So this one, they don't have the correct name, but this is linear now. PCL5 has a bond angle of approximately 120. Where is it? PCL5. Yes, that is correct. And same, they did not include the tellurium as well. As you can see here, there is that bond angle of 120. It even says here, for even the seesaw, 120 in the plane and 90 above and below. So kind of like right there. This is 120. Around there, theoretically, even though it is going to be less because of the electron there. KRCl4 exhibits that sp3d2 hybridization. But not only is it KRCl4, but it's also the ICL5. And TeCl4 has square planar. That is correct. And whoops, no, that is not correct. It's the KRCl4, so that's incorrect. And TCl4 and ICL5 are polar. That one is actually correct because of the lone pairs that don't cancel each other out there. So overall, this is incorrect this is, I'll say, partially correct. So TeCl4 is seesaw, and what else did they miss? So let's start from the top. So TeCl4 is seesaw. Okay. Where is it? KRCl4 is square planar. Where is it? Oh, there. TeCl4 also has a bond angle of approximately 120 degrees. What else did we put? Okay, ICL5 also has a sp3d2 hybridization. Okay, I think that was everything. Yeah, I think that's everything that they covered here. And just to make sure exactly, when we're dealing with octahedral, looking at the Vesper theory, as you can see here, sp3d2, which was also ICL5 because of the because of the 5:1 ratio that it had. Because it even shows here, just to make sure I'm not seeing anything wrong, 5 bonds, 1 single pair, that is actually 6. So that's why it's sp3d2 there. Okay, so that was that. I'm gonna kind of do this for you in case you want to just pause and just stare at these beautiful pictures. Just make sure that you have the whole concept here of what we went over and which of these had the answers we were looking for. Okay, so with that, let's move on to question number 9. Hopefully you had enough time to pause and just kind of review that. Oops. Whoops. There we go. So question number, I think I zoomed in too much. There. Question number 9. What is a formula for potassium nitride? Okay. So for this, we have to know what we're dealing with in regards to what they mean by nitride and potassium. Potassium is relatively straightforward because we just get it straight from its name. Okay, so that one would just be K. Nitride, though, that one's a little bit trickier because it's actually going to be, the rule is that if it ends in IDE, it's typically just the element by itself. And what element? The nitr part, NITR, which is actually just nitrogen. Okay, So we have a potassium and a nitrogen, okay? If it was like nitrate, that'd be NO3, which is completely different. That's a different ion. Nitride, we're only dealing with nitrogen ions, okay? So with that being said, we have to figure out, you know, what the actual bond distribution will be. So with that, nitrogen, okay, has, it's on the 15th column, meaning that it have 5 electrons. So to get to its filled shell, it'll just rather add 3 than remove 5. You can also support this through the electron configuration. Okay, start at helium and be 2s2 2p3. This also supports that it has 5 in its valence shell. With that being said, it wants to then just add 3 more rather than get rid of all those 5. Potassium, on the other hand, all the way over here in the 4th row. So with that being said, you know, we have argon, okay, and then we just have 4s1. So now we have 4s1, 2s2, 2p3. In total, for potassium, it only has 1 valence. Nitrogen, 5 valence. Potassium has an easier time getting rid of 1. So typically a potassium ion would just be K+. As we discussed, nitrogen wants to add 3. And if you remember, adding electrons means that you actually have a negative sign, so 3 minus. For this to be a neutral compound, we need to have the same amount of positive and negative charges. So with that being said, we need 3 of these K's to make up for the 3 negative on the nitrogen. So we have K3N. This is a formula for potassium nitride, okay? So with that being said, as we look at the answer, K3N is a chemical formula. Oh wow, it actually does even go through the electron configuration. I thought I was the only one doing it. I'm glad it answered the question like that, because I personally love just emphasizing the electron configuration. So with that being said, on the other hand, nitrogen, yep, 2s2 2p3 shows that it has 5, and because it'd be easier to just add 3 more to become the octet, that's what it does. So when it forms together, we have K3N. It's nice to even give us the molar mass, which is calculated by adding the atomic masses of 3 potassiums and 1 nitrogen. And these are just some reactions that are involved. But overall, this right here is correct. So hopefully you understand how we got potassium nitride. We first have to understand what the IDE meant for the nitride, okay, which is where we just gave it to get the nitrogen. And then we balance the charges based on where they were on the periodic table / their electron configuration. So now let's move on to question 10, okay? We have determined whether CHClO is an ionic or molecular compound and draw an appropriate Lewis structure. So CHClO. All right. So is it ionic or molecular? And then draw Lewis. Okay. So with this, we can actually answer whether it's ionic or molecular fairly straightforward. Do you see any nonmetals? Well, carbon, hydrogen, chlorine, and oxygen are all nonmetal, 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 and hydrogen over here, nonmetal. Okay, so all these are nonmetals. Now, do you see any metals? Well, no. So this would actually just be a molecular bond, well, a molecular compound, because there's no metals present. There's no metal ions. Okay. Now, let's draw the Lewis structure. Okay, we have CHClO. So first we find out the specifically the amount of electrons each contributes. Carbon being on the 14th column, and also the electron configuration being 2s2 2p2. It supports that it only gives 4 electrons to this. Hydrogen is just 1s1, so it only gives one electron. And I'm getting these numbers for electron configuration based on the row, based on the column they're in, and also the row. But chlorine is down here, the 17th element. Okay, so if we count through, we start from the most recent noble gas, and then it'll be 3s2, 3p5, which also supports that chlorine has 7 valence electrons to work with. And oxygen, the last one, okay, start at helium because it's close to that carbon, and 2s2, 2p4. All right, so that means oxygen has 6 electrons to give. So in total we have 4 plus 1 plus 7 plus 6, and we get 18. So we're working with 18 electrons. All right, and because carbon, okay, is kind of like the best one to work with because it has 4 lone electrons, it can form pairs with each of the electron. We'll put that in the middle. So we have C right here. All right, and this is where it gets a little bit tricky because we want it to be, ooh, yes, I'm going to CHClO. I'm really thinking about this one because I believe, let's start like this. You know what? Let's just continue with our gut. Okay. So it's gonna have Cl. Oh, there's only 3 things. Wow, I'm really bad at counting. No wonder I was panicking. Good. That makes things a lot easier on my head. So Cl, H, and O. And chlorine, as you said, it likes 7 in its valence electrons, and it's only sharing 1 of its 7. So 2, 3, 4, 5, 6, 7. Hydrogen is already sharing 1 of its 1. Oxygen is sharing right now 1 of its 6. So 2, 3, 4, 5, 6. And carbon is sharing, actually let me draw like this. Carbon is sharing 3 of its 4 right now, okay? So it's 3, 4. So what's going to happen here actually to be able to satisfy this octet rule and just work with each other, these are going to form a double bond, okay? So now what we have as a picture for a Lewis structure is carbon, chlorine, a double bond here for the oxygen, and whoops, no longer here, the hydrogen right here. Then we fill out the valence electrons, okay, and then we are done there. Okay, so now with this all being said, okay, we're going to now figure out the theoretical charge of each one. So chlorine has is going to be like 7 valence electrons. Subtract, it has 6 electrons by itself and is bonded, sharing 2 more, so that's why you divide it by 2. That does equal 0. The carbon in the middle, 4 valence electrons, it has 0 by itself and is sharing 8 of them, so that's also 0, so that's perfect for the theoretical charge. Oxygen, 6, okay, it has 4 by itself, is also sharing 4, so that's also 0, so it's perfect. And hydrogen is 1 and it's sharing 2. So all these are perfectly balanced. This right here is the Lewis structure for CHClO, okay, and it'll look like this with bonds, okay, with carbon in the middle, Cl, oxygen, and then hydrogen right there. That's what that would look like with just the bonds. But yeah, this would be the Lewis structure of that. Okay, exactly. So you see here 4, 1, 7, 6, 18 valence electrons, and this is what we get. to a double bond where the oxygen is, single bond is everyone else, and CHClO is a molecular compound because of the fact that there are no metals there. Okay, so now question number 11. What is the difference between atomic mass and molar mass? And molar mass, okay? So the key difference here, actually, it honestly depends on what type of compound you are dealing with or element. So atomic mass, okay, starting there, atomic mass is strictly the number on the periodic table. Okay, so with that being said, the atomic mass, okay, if you look at the periodic table, when they give you the atomic mass units, it's right here at the bottom. Okay, lithium, atomic mass of 6.94, beryllium, 9.0122, oxygen, atomic mass 15.999. That is what atomic mass means. Molar mass now, okay, all right, is the addition of, let me actually draw a different color, is the addition of atomic masses. Now, what do I mean by that? Is that sometimes you're just adding just one thing. If I said, what is the molar mass of potassium, okay? Just potassium. Potassium in nature just shows by itself, okay, solid. Okay, that is its form. So the molar mass would be the addition of one potassium. That's just it. So you look at the periodic table, and one potassium, this atomic mass is just 39.098. So in this case, like when dealing with this solid, well, not solid, when dealing with this metal, or even like noble gases, for example. So metals and noble gases usually follow this trend to where the molar mass is really just the atomic mass. Now, if I said, what is a molar mass of oxygen? That's different. If I said, what is the atomic mass of oxygen, you would tell me that it's just 15.999, because that is the number on the periodic table, one oxygen atom. Molar mass now implies in terms of what it shows up as nature, and oxygen in nature is O2. So now, instead of it being one krypton like what we have here, we have two of the atomic masses of oxygen. So the molar mass of oxygen is actually 31.998, because oxygen shows up as a molecule in nature. That is its molecular structure, O2. And you will typically see this with like gases like fluorine, chlorine, excluding noble gases though, but like oxygen, fluorine, chlorine, those things, when they say what is a molar mass, you're no longer dealing with one element, okay? And with that being said, you would also, or should specifically, you should never see something like what is the atomic mass of CH3Cl. This cannot have an atomic mass because it's composed of different elements. There is no CH3Cl on the periodic table. What it should be asking for is a molar mass, because that allows us to add up our atomic masses to get the answer. So the molar mass of this, for example, would be 1C plus 3 hydrogen plus 1 Cl. Adding those atomic masses is what gives us our molar mass, okay? So that is the difference between molar mass and atomic mass. And let's see what they have here. Atomic mass is expressed by atomic mass units, And they also explain actually how they got the atomic mass numbers is that they actually take the isotopes, because if you see in nature, you won't really see a carbon that has, I guess, 12.011 grams. Usually you see a mixture of different isotopes of carbon, okay, where they have specifically 6 neutrons, 6 protons, which adds to around 12 atomic mass units. Okay, electrons are so insignificant they don't really factor in. But point being is that you have some carbons like that, and you have other carbons that still have 6 protons but 7 neutrons. So what they do is that they take the percentage of the carbons present, which is what they explain here, and that's how they get that atomic mass unit. But the molar mass, as they go forward, is the grams of 1 mole of a substance, and you have to now add up the atomic masses of the compounds of the things it's composed of to get the molar mass. For the elements, though, like they say, like we discussed metals and the noble gases and such, the mass, molar mass and atomic mass are equal, like how we discovered here. But for certain other elements, okay, well, they're not really called elements anymore. They are called molecular elements, but like the gases, oxygen, fluorine gas, chlorine gas, that one would actually be different in regards to their molar and atomic mass because of the fact that they don't, the molar, I guess, formula is written as O2F2Cl2 and no longer the same as just the atomic mass. But yeah. And now for this, we're going to solve question 12. And I'm going to stop here after this question just because we did deal with quite a big question earlier, but let's focus now on what we have here, which is give systematic names. And this one might take a while too. Systematic names to following compounds. Okay? And these are binary compounds, which is so A, B, C, D. We have N2F2, CF4, N2O5, and AS4O6. So the way we name these, that first we have to recognize something. As we go through them, which is what I'm going to do right now, you notice that all of these are molecular compounds because nitrogen and fluorine, they're both nonmetals. Carbon and fluorine, so this is molecular. Okay, carbon and fluorine, same thing, both nonmetals, molecular. Nitrogen and oxygen, both nonmetals, molecular. Okay, acetine and arsenic, that's what it is. Arsenic and oxygen, both. Ooh, that's tricky. It's metalloid. We're gonna say that this is, well, let's see. Arsenic and oxygen. Let's find out by its electronegativity. 3.44 minus 2.18. Oof, jeez. 1.26 difference. We're gonna say this is molecular as well. There may be a better name, but we're gonna name all these. Oh, that's metalloids are always the trickiest ones because they're kind of metals but kind of not, so their naming gets a little bit complicated. But we're gonna go with the trend here and name them by like molecular standards. And the key thing about molecular naming is that you want to include the prefix indicating how many you have. Okay, so starting with N2F2, this would be dinitrogen difluoride, and you still end with IDE because that is what you do for the second half. You still end with IDE. You always drop the N. It's not going to be fluorine anymore. It's going to end with IDE, so dinitrogen fluoride. Okay, and now CF4, we have carbon, and the naming always applies at least to the second one, but the first one, if there's a number there associated, Okay, in this case there isn't, but if there was, you'd be like dinitrogen, dicarbon, tricarbon, things like that. But here we only have one carbon, so you don't have to. You can say monocarbon, but I would recommend you don't, because the important part is the second one that follows. Okay, so the carbon tetrafluoride. Okay. Alright, still the same IDE. And the funny thing is that actually this one is also known as methane, because that would be its hydrocarbon naming rule. Okay, definitely not methane. I thought I was CH4. CF4. This is carbon tetrafluoride. Please don't make the mistake. This is not methane. So with that being said, we have carbon tetrafluoride. This one here, N2O5, this would be dinitrogen pentoxide. Okay, and the last one, because we're just assuming molecular, I don't even know if this is correct. I'm going to say it's tetra-arsenic. So tetra-arsenic, which is a mouthful. Tetra-arsenic hexoxide. That looks very wrong to me. But what can we do? These are the names we're going with. Let's see how we did. So yes, N2F2, dinitrogen difluoride. Awesome, we got that. Carbon CF4, carbon tetrafluoride. Perfect. N2O5, dinitrogen pentoxide. Awesome again. And now, moment of truth. Arsenic trioxide. I couldn't tell you why. No, really, I can't. What they did here is that they took it down to its, I guess, base, which is this, AS2O3, and then they named it. But then if that was the case, we could say this was nitrogen fluoride, which is not true. You can't just do that to anything. And I think this is where it ties into the fact that it's a metalloid, because it kind of follows the, yeah, you see, it literally is a metal, like a pseudo metal, because it literally half follows the rule. Because here they dropped the fact that arsenic should have like a di in front of it, but then they still have the trioxide at the end. Because for ionic compounds, when you name them, you don't even put the I guess the prefix there at all. Like when you have a good example would be CaCl2. Okay, this is just called carbon chloride. Okay, I mean, whoops, calcium chloride, not carbon. Yeah, this is just called calcium chloride. In fact, if I were to search it up, it'd just be calcium chloride, and you'll see it here, CaCl2. Okay, but if I were to search up, so exactly right now we have arsenic trioxide, which literally breaks almost every rule we know so far about naming, which makes sense because it's a metalloid. It does what it wants. Unfortunately, this would be one of those you kind of have to memorize. But if I were to type in wrong place. If I were to type in tetraarsenic hexoxide, it shows up. You see, AS406. Yeah, so it's a real thing, but if I click this, it calls it arsenic trioxide. So it has multiple names. And it looks like I did spell it wrong, because you should actually have an extra A. I thought you could kind of drop it, but I guess it really likes to be tetraarsenic. So this one I'd highlight because systematic, according to Google, it works for this. You can still get tetraarsenic hexoxide, but its other name is also known as arsenic trioxide. So with this type of question, this is correct. it's just really tricky when you're dealing with metalloids. Those ones, hopefully you don't get those type of questions, but I would treat metalloids like just nonmetals. Even what I did there when I calculated the electronegativity difference, if it stays below 1.6 difference, to me that is not going to be ionic. That's a molecular type of bond, if that makes sense. Okay, so with that being said, this is correct, and we're going to solve that, and we're going to actually stop here. So just want to thank you again for joining us this stream. If you have any further questions or want to explore in greater depth and detail the questions we've gone over, definitely I implore you to check out the links below. Other than that though, you have a great rest of your day, and see you next time.